Welcome. This is 49J5 and we're going to talk about charging and discharging an RC circuit. So we're going back and bringing capacitors and we're combining them with resistors. So let's just draw this circuit out and talk about it for a few minutes. So we have some kind of power supply, and then we have some kind of resistor, and then we have a capacitor, and then somewhere we have a switch, and the capacitor begins being uncharged, and then we close the switch and we start adding charge onto the capacitor plates, and as time passes we add more charge onto the capacitor plates, and eventually it's fully charged. Fair enough. Now we could ask a little bit more detail here and say, hold on, let's say we have 10 volts. As soon as I close the switch, is the 10 volts applied to the resistor, or is the 10 volts applied to the capacitor, or do they both get 10 volts, or what have you? And remember, we say, well, the wires can't support a potential difference, so this is all no potential drop, and this is all no potential drop. And so the 10 volts is applied between here and here. That's 10 volts. But again, does the resistor get it all to begin with, or does the capacitor get it all to begin with? And so we have to think about our equations, and the two equations we have is delta V is equal to IR, and C is equal to Q over delta V, so delta V is equal to QC. Now, is that voltage difference causing that charge, or is that charge causing that voltage difference? And it's a bit of a chicken and an egg situation, but the best way to think about it here is that as the charge builds up, the potential difference increases on the capacitor. So initially there is no potential difference across the capacitor because there's no charge, which means initially all the voltage is across the resistor and there's none across the capacitor. Well, if there's a big voltage across the resistor, there's a big current flowing, and so we get a lot of current flowing down here. That quickly enables us to start adding charge, and as we start adding charge, the voltage across the capacitor increases, and so the voltage across the resistor decreases. As the voltage across the resistor decreases, there's less current flow, so the charging becomes slower. And you can imagine a situation, I won't do them all, but we'll have 5 and 5, and then we might have 7 and 2, 7 and 3 make 10, and then we might have 10 and 0. So in the end, all the voltage is across the capacitor because it is fully charged, and there's no voltage across the resistor and there's no current flowing. So this is a dynamic situation. It's got a certain speed, a certain time for this job to be done, and that time depends upon, well, the EMF of the power supply, the resistor value, and the capacitor value. If we apply Kirchhoff's rules to RC circuits, we don't actually know the Kirchhoff's rules for a capacitor, but it's basically the same rule we applied to the EMF. If we apply Kirchhoff's rules to an RC circuit, we can determine how quickly a capacitor charges up or discharges. It turns out it's a differential equation, and that's mathematically beyond where we are. in this course. So we kind of pull the answer out of a hat and we say for charging up at time t equals 0 seconds, just after you close the switch, as we just said, there's no charge on the capacitor, and then at time t equals somewhere in between times t seconds, well, the charge is equal to the maximum charge possible, which is the EMF times the capacitance, modified by 1 minus e to the minus the time over a constant called the time constant, which equals RC. And then at very long times, I said infinite seconds here, we find that it's fully charged, and so this part becomes 1, and we end up with the charges, the EMF times the capacitance. And I can visualize this with a graph, and we see that this thing is steadily increasing. The rate of charging is slowing. We said that because there was less and less potential difference across the resistor. The current flow was less and less, and so the rate of charging was slowing. It's useful to have a handle on these things, and what we find is that e to the minus 1 is a significant value, and so we find that occurs when the time is equal to the product of the resistor's value and the capacitor's value. So we define this thing called a time constant, tau, and the time constant is the time it takes you to get to about 63% of the fully charged value. So we remember time constant. It's very nice. I can look at a circuit and say, let's have a look. I can say the resistor is 6 ohms, and I can say the capacitor is 5 farads. That's going to be a time constant of 30 seconds. It's going to take 30 seconds for the charging to reach 63% of its maximum value. It's a very nice way of calibrating, estimating what's going to happen. If I take a charged, let's go back to the previous page. If I take a fully charged capacitor, and what I do is I open, I don't know if I can do this without erasing half my diagram, but if I open that switch, now that charge is trapped and nothing's going to happen basically. But if I, let's see if I can do this, if I short out that part of the circuit, now the battery's on a dead end, so nothing happens to it, but now current can flow around this loop, and so the positives try to match up with the negatives. It's got to go through the resistor. I'm not just shorting out the capacitor, I'm shorting out the RC combination. And if that happens, then I start off with a fully charged capacitor, and I steadily decrease. And again, this time constant is very important, and it's the time required to get 63% discharged, which is 37% charged. And so we have this similar equation. It's the maximum value multiplied by this factor. So when you're discharging at time t equals 0, you're still fully charged, and then you have a decreasing charge until you get to infinite time and you have no charge left on your capacitor. Let's look at some questions on this. This circuit on the right consists of a 6-volt battery, a 3 farad capacitor, and a 4 ohm resistor. The capacitor is initially uncharged and switch S is open. What is the potential difference across the capacitor immediately after the switch is closed? Now remember, the 6 volts EMF is there all the time. As soon as we close that switch though, we have no charge on the capacitor, so there can be no potential difference across the capacitor, because we said C is equal to Q over delta V. So delta V is equal to Q over C. No charge, no delta V. So what's the potential difference across the capacitor immediately after the switch is closed? 0 volts. So what's the potential difference across the resistor? That would be 6 volts, because it's a 6 volts EMF. What is the time constant of the circuit? My time constant equals RC, which equals 4 times 3, which equals 12 seconds. It takes 12 seconds to get to 63% of the fully charged condition. How long will it take the capacitor to get to 63% charged? 12 seconds. It's the time constant. It's a very useful thing. What is the potential difference across the capacitor 20 minutes after switch S is closed? I don't need an equation to sort that out. When I first start, I have no voltage across the capacitor, and all the voltage is across the resistor. And then as I build up more and more charge on the capacitor, I get more and more voltage, and I get less and less voltage available for the resistor. And finally, when I'm fully charged, all the applied voltage is across the capacitor, and none of it is available across the resistor, so no current flows. And so it's a very long time this thing is fully charged, and it's fully charged, and my voltage is going to be 6 volts. It's the maximum available. Let's look at this next bit. This circuit consists of a 6 volt EMF, a 3 farad capacitor, and a 4 ohm resistor. It's the same circuit. What is the potential difference across the capacitor 14 seconds after switch S is closed? So I can say, okay, well let's begin by saying that C is equal to Q over delta V. So I can say, so I can say delta V equals Q over C, and I want to find my Q at 14 seconds after the switch is closed. So Q is equal to, well, it's going to be the maximum Q, which is EMF times C, and then I'm going to have 1 minus e to the minus t over tau. So my Q is equal to EC 1 minus e to the minus t over RC, because that's what my time constant is for this circuit. Let's put some numbers in. So this is going to be 6 times 3, 1 minus e to the minus t. T is going to be 14 seconds over RC, and RC, can you see, R is 4 and C is 12 and C is 3, so that's going to be 12. So the way I like to do this is I do it bit by bit. So I'm going to say that's going to be 14 divided by 12. It says 2 at the minute. We'll make that into a 12 so we don't make mistakes. 4 3s are 12. So 14 divided by 12 equals, and then I'm going to say, second e to the x, little minus second answer, and that gives me 0.31. 1 minus second answer. I've done everything inside the bracket. times 18. 6 threes are 18 times 18. So Q is equal to 12.4 coulombs. And if I want to know my potential difference, my delta V is equal to Q over C, which equals 12.4 divided by 3, which equals 4.1 volts, basically. And let's just think about things. So this is Q and this is T, and my point of interest is just beyond the time constant. Time constant is 3 fours are 12, so there's 12. That's how long it takes to get to 63%. And that would be 63% of fully charged. And I'm a little bit more than 3%, 63% of fully charged. And then the maximum voltage I could have is 6 volts, and I got 4.1 volts, and that seems to make sense to me. So I'm happy with that. So there we have it.